All right, everybody, welcome to lesson 5-9, lesson 9 in unit 5. We have one more lesson, and then after that, we're going to have a quiz. So, probably a quiz on Thursday ish would be my guess. Maybe Friday, we'll see. Okay, let's model situations with linear functions. So, we're just kind of doing some word problems with functions now. Lesson or activity 1 says a candle is burning. It starts at 12 inches. After an hour, it's 10 inches. And then after 3 hours, it's 5.5 inches. When do you think the candle will burn out? And is the height of the candle a function of time? So I'm going to answer this a little bit backwards. So I'm going to start with 2. And I'm going to say, well, for every specific time, so for each time, there's one height. So yes, it's a function. Number 1 wants me to guess when the candle will burn out. So let's say that it's a candle. Say that's my candle, and that from here to here is 12 initially. 1 hour goes by, and then it's a little bit shorter. Now from here to here is 10. So it lost 2 inches per hour. So if we say it loses 2 inches in 1 hour, then after 3 hours, I could say, oh no, what does it say? What do you think when it'll burn? Okay, so after 3 hours, it's 5.5 inches. So we could just do 12 divided by 2 equals 6, and then I could say 6 hours. It's kind of a fast way to do that problem. Okay, activity 2, shadows. The sun was directly overhead and the stick had no shadow. After 20 minutes, the shadow was 10.5 centimeters. After 60 minutes, it was 26 centimeters. So we're talking about this being 10 and this being, that's kind of hard to see. This is 10. This is 26 centimeters. Okay. The shadow, not the height of the pole or whatever that is. Based on this information, estimate how long it will be after 95 minutes. So we can kind of use the information that's there to help us come up with like what we did with the candle. So if after 20 minutes it's 10.5 centimeters and after 60 minutes it's 26, we could do, can I pull up a calculator? No, I can't. That's annoying. Okay, I'll do it over on my computer. So let's see, what is it? 20, okay, after 60 minutes. So if I just did 60 divided by 26, I'd get 2.3. So that could be one rate, 2.3. That's 2.3 centimeters per minute, I guess. And then 20 minutes, 10.5. So if I did 20 divided by 10.5, I should get a very similar number. I get 1.9. So that's 1.9. So I could pick somewhere in between 1.9 and 2.3 and just like settle on 2. So if I say that it's burning I'm thinking about the candle problem still. The shadow is gaining length by 2-ish centimeters per minute, then it wants to know after 95 minutes. So I could do 95 divided by 2. So this isn't like, I'm being lazy and I'm not writing a formula really, but So 47.5 inches or centimeters, sorry. But this is probably what you would do if you were doing this on a standardized test. I don't really think you'd be writing a formula. Okay, so that's our guess. After 95 minutes, they're saying in number 2 that the shadow, based on estimate, how long would it be after 95? So they're saying they got 38.5. How does this compare to your estimate? So we are 10 centimeters off. So what happened? Our prediction is pretty close to correct. We could say we overestimated. We just overestimated. So we overestimated. So, with the information we had, though, getting 47.5, or maybe you were a little bit closer to 50, that makes sense based on the information given, because we didn't, that's all that we knew. So that's fine, and that is what your answer should be. And I just checked the answer key, and it actually is that we'd be about 10 off. So for some reason, some of them just don't line up. The way that you would guess something to be turns out differently, and that's fine because it wasn't enough information to guess accurately is pretty much what that tells you. It doesn't mean you're wrong. Is the length of shadow a function of time? If so, is it linear? Explain your reasoning. I would say that yes, it is. So yes, because for each time there is one length. So remember, one input, one output. That's pretty much what you have to ask yourself. Is it linear? Well, based on the fact that it was a little bit difficult for us to predict, I'm going to say no, because that means that would have been more of a plugging something in and getting perfect answers. So probably not linear. But if we were in class, we would have used a graphing application and we could have graphed it, but we're not going to do that now. That's just too much work. So anyway, it's not linear, because if you were to make an equation and plug the points in, they would kind of be it'd look like this picture in the next problem. It would be very difficult to draw a line through all the points. That means it's not linear. Linear is they all line up. Okay. Anyway, activity 3. Sketch a linear function that models a change. Okay. Anyway, in an earlier lesson, we saw this graph. I think it was last lesson, that shows a percentage of garbage in the U.S. that was recycled between 91 and 2013. Okay, so number 1 wants you to sketch a function that models a change in the percentage of garbage that was recycled between 91 and 95. Which years does the model do well at predicting, and which years is it not so good? So for this, I don't think you need to write. I think you just draw. Okay, yeah. So you can use a highlighter, your pencil, whatever. So between 91 and 95, I'm going to kind of draw a line, something like that. You know what? Let's not use a highlighter. That's not going to work as well. And it's so hard to draw a straight line the way I want to draw it on this dumb iPad. Okay. These points I put blue dots above are the 2 points I'm trying to aim my line through, but it's just, okay, there we go. Just pretend that's going through those points. Here and here. Okay. That's more or less what it would look like. You have some outliers. So which years is the model good at predicting and which is it bad? So it looks like between, we could say 1991 to, 1993, not so good, because the dots are off the line. And then you could say it's better, between 94 and 95 or something like that. It doesn't need to be perfect. Okay. Cool. What does number 2 want? Pick another time period to model with, and this one you can do on your own. So this one you're going to try on your own. Pick another time period to model with a sketch of a linear function. So you're going to pick another series of dots and you're going to draw a line, you know, like you're going to draw a line somewhere through here. Oops, not that one, that one. Something like that. And then you're going to write, oh, it's good. These years are good because it's going really close to my line or through my line. These years are bad because they're just totally off. That's what you're going to do for that. And look, we're already done. No way. Really? Oh, guess we're done. Okay, cool. Remember, and I'll write on this blank page, 11:35 to 12:05 is help. And then please do practice problems.